lesson 10.2, we are going to look at what logarithms are and also what logarithmic functions are. We're going to find out that a logarithm is really an exponent. That's what you want to think of it as. So here's a question for you. Why is logarithmic scale used to measure sound? And they go into details here. Many scientific measurements have such an enormous range of possible values that it makes sense to write them as powers of 10 and simply keep track of their exponents. For example, the loudness of sound is measured in units called decibels. You've probably heard that. The graph shows the relative intensities in decibel measures of common sounds. So for example, a pin dropping, the relative intensity is 10 to the 0 power. The decibels are 0, so it's the exponent on the relative intensity. This would be like whispering. Relative intensity is 10 squared. 20 decibels. Okay, so there, it's the exponent multiplied by 10, basically, for the decibels. Here, 10 to the 4th would be 40 decibels, because you take the exponent times 4. Just normal conversation. Relative intensity, 10 to the 6th. And then you take that exponent 6 times 10, that's 60 decibels. All the way over, noisy kitchen, jet engine, 10 to the 12th. So if I take that exponent of 12, multiply it by 10, it's 120 decibels. The decibel measure of the loudness of a sound is the exponent or logarithm of its relative intensity multiplied by 10. So exponent and logarithm are synonyms. They mean the same thing. And that's what we want to keep in mind as we go through the lesson here. Alright, we're going to look at forms here, two different forms. We have logarithmic form and then exponential form. Let's look at the exponential form first. If I have that x, some number x, is equal to b to a power of a. So a is your power, the base is b, that's why we put a b there. Okay, I want you to look over to this as far as where things go. When we write, and logarithm is abbreviated with log, notice this base right here is the little subscript after the word log. So it's a log with a subscript of b. The exponent, or the power, okay, that was on that b is over here on this side. And then what it's equal to is right there. What you're taking the log of. Okay, now it's not going to make a whole lot of sense till we look at some problems here. Before we get to going from logarithmic form to exponential form and then from exponential form to logarithmic form with some examples, a couple things about some of those letters or variables that are involved there. B, or the base, has to be bigger than 0. It also cannot be 1. And x has to be bigger than 0. So in other words, right here, this value, the thing you're taking the log of, and we'll get into details so that becomes clearer for you, that must be a positive. Okay, it must be bigger than 0. So what they're asking us to do here is to go from logarithmic form to exponential form. So we're going to, as you can see, all these are written with logs. Okay, some have numbers, some have, we're going from one form to the other. Okay, so here's what you want to say. This is like your x, this is your b, and this is your a if you're looking at the forms up above here. So what I want to say is, okay, and it doesn't matter what side you put your x on. So I could say b to a power of a equals x, or x equals b to a power of a. I personally like to take my base to the power first. So I'm going to say 8, that base of 8, this is the exponent, to the second power equals 64. You could have said 64 equals 8 squared. Either way. Now, that's obviously a true statement. So the log of 64 in base 8 is equal to 2, because I would take that base 8 and take it to the second power to get 64. Okay, so this would be writing it in exponential form. Exponential form means you're writing it as a number to a power equals some other number. So if I go here, I'm going to take my base of 16. Here's the exponent. Okay, so that's the base. There's the exponent, and there's what I'm going to call it the answer. So I'm going to take 16 to the 1/2 power, and that has to equal 4. Or you could have said 4 equals 16 to the 1/2. And if you think about this, this right here really means 1/2 power means square root 16 from what we've learned. And the square root 16 is 4. So that is a true statement. But writing it in exponential form would just be writing 16 to the 1/2 is equal to 4, or 4 equals 16 to the 1/2. Okay, now we get over here and we start throwing some letters in there and some expressions. It's no different. You're going to take the base q, raise it to this exponent. Q to the power of t has to equal the answer of 7, or 7 equals q to the t. So here, I'm going to take my base. So I'm going to call that the b. So I'm going to take x plus 2. Now, if you notice, that has two terms on it, so I got to put parentheses around it. This is the exponent, or the power. So to a power of st equals, and that's going to go over there, which is a squared plus b squared. Now, you can keep the parentheses on. You don't really have to, because that's just, you have those two terms on that side. It's not really multiplied by anything or taken to a power on that side. So you don't have to have the parentheses on the right side. On the left side, you do, around the x plus 2. So that's going from logarithmic to exponential. Now let's look at going the other way. So now we're going to write these with LOGs. So the LOG, okay, remember, I think this was our logarithmic form. So this is the base. This is the, okay, so the base we're going to take, it's going to be the log of 27, base 27. A is the exponent, so the 1/3 is going to go over here. And, whoops, I don't want that to be a 2. That needs to be a 3 there. So the log of 3 in base 27 is equal to 1/3. That would be writing it in logarithmic form. So the base becomes the little subscript. This is what's right after the word log in the base, and the power, or the exponent, goes over on that side. So if we do that here, this is going to be log of base 10, because that's what's raised to the power, of 100 is equal to 2. Remember, the exponent goes over on that side, the non-log side. Here's the base. That goes down here as the subscript. And that goes there. So this would be the log in base x of 12 is equal to the exponent, or the power, which is a. This would be the log of base a plus b, and you can put parentheses around it if you want to there, of 84x plus y. Now that has two terms, so that must have parentheses, and I think it's maybe a good idea to put it on the base there too, equals the power, which is 7x. So all I'm doing is going from exponential to logarithmic form there. All right, now let's look at actually evaluating some logs. We want to find out what this is equal to, so I'm going to draw an empty box there. So I really want to say this is my base. This is, if you think about from logarithmic form to exponential, that's the exponent. So 10 to some power, I'm going to call it 10 to an empty box power, equals the answer of 1,000. Well, 10 squared is 100, 10 to the third, so the empty box would equal 3. So your answer here, the log of 1,000 in base 10 is equal to 3. You just got to kind of think about it, and I'm going to use kind of this empty box as we go along here. Empty box. So we're going to say 2 to what power, because that's the exponent. This is the base, and then this is what that has to equal. Well, think about it. 2 to the second power is 4, 2 to the third power. So in other words, the log of 8 in base 2 is 3, because that's the exponent that would have to go on that base 2 to get 8. Over here, here's the base. 9 to what power is equal to 3? Now, notice 9 to the first power is 9, 9 squared is 81. We got a number smaller than that. So now I got to start thinking about roots and fractional exponents. 3 is the square root of 9. So 9 to the, and square root means, remember square root means something to the 1/2 power. So really, this is going to be 1/2. 9 to the 1/2, or the square root of 9, is 3. Over here, now we have the log of -5 in base 8. What's that equal to? So we need to go 8 to what power equals -5. Okay? We can't, I mean, if you think about that, you can't do that. And remember what we said about what you're taking the log of. This can't be negative. That number right there has to be bigger than 0, and it's not. So that's impossible. You can't do that. You can't take the log of some negative. So if there's a negative number after the log in the base, you can't do it. It's impossible. Okay, that has to be a positive number there. Over here, log of 1 in base 8. 8 to what power is equal to 1? Now you got to do a little thinking here. Anything to the 0 power is 1, so the answer here would be 0. The exponent on 8 would be 0 to get 1. All right, then we're going to look at the inverse property here. Inverse is, to give you an example of inverse, addition and subtraction are inverses. They undo each other. Division and multiplication are inverses of each other. Okay, squaring something, taking the square root are inverses of each other. Okay, so what you want to do here is it's going to kind of be canceling out. So if I have, let's just look at this using the empty box that I just did. I would say 6, this base, to this exponent. 6 to what power is equal to 6 to the 8th? Well, if you think about what has to go in the empty box there, it's got to be an 8. 6 to the 8th would equal, so that would have to be 8. So the answer here is 8. So let's retake a look at this. Let me change colors here. But if I have the log of in base 6 of 6 to the 8th, if this is the same, the base, and then you're taking you're taking that base to a power, this is always going to be the answer here. So if I had the log in base 5 of 5 to the 3rd power, the answer is 3. These things kind of cancel out right here. Okay, so just to give you another example. Here, I have 3 to the log base 3 of 4x minus 1. Now you're taking, notice if these two match right here, okay, these are kind of inverses of each other, and that's going to be your answer. Okay, in this case, it's just an expression. But to give you another example, if I have 5 to a power with log base 5 of 15, 5 to a log base 5 power, that cancels out, leaves me with just 15. If I have 8 to the log base 8 of 250, this cancels out. Your answer is 250. They are inverses of each other, kind of like square and square root, addition, subtraction, and so on, multiplication, division. Okay? All right, solving a logarithmic equation. Here, this is we've kind of been doing this. Now, this is in logarithmic form. So here's the base, 8. This is the exponent or the power, what the logarithm is equal to. So 8 to the 4/3 power has to equal n. Okay, now, 8 to the 4/3, you could on your calculator do 8 to the 4/3 power and get your answer. But remember, 4/3 power means the cubed root of 8. So this bottom number is the root. And then you want to take that result and you want to raise it to the 4th power. Well, the cubed root of 8 is 2. So I want to take 2 to the 4th power. So my answer for n is 16. Okay, you take the cube root of 8, because that's the bottom number in the rational expression or rational exponent, and then you raise it to the 4th power. So it is 16. The log of 16 in base 8 is 4/3. And you'd get that on your calculator if you actually did this right here. Okay, let's go over to this one. So here I'm going to do 27, this base, to this exponent, or power, is equal to n. So if I do the cubed root of 27 and raise that to the second power, well, the cubed root of 27 is 3. 3 squared is 9. So in this problem right here, n is going to be 9. What that means is the log of 9 in base 27 is equal to 2/3. Okay, some key things here. Solving a logarithmic inequality. Notice the base has to be bigger than 1. And what you're taking the log of has to be bigger than 0 on both these cases. These two things are true right here. So let's look at these examples. So if I have the log of x in base 2 is greater than 3, when I write my inequality, I take that x, put that there, and that keep the symbol the same, and then I put the base to the power. So the base to the power over on this side. Okay? If it's less than, remember, this has to be a positive number. So we do have a low end on the interval here. We know it can't be less than 0. So I would say 0 is less than x, which is less than 3 to the 5th power. Okay? So we're kind of using those two right here. So here's what I want to do. I want to take, this is a greater than 1. I want to take that x, and I want to say, well, that has to be bigger than this base of 6 to this exponent of 3. So x is bigger than 6 to the 3rd, and if you actually take 6 to the 3rd, it's 216. Over here, now it's a less than. The log is less than, so we're going to have 0 on this side is less than. We're going to put the x right here, which is less than the base of 3 to this exponent squared. So really you have 0 is less than x, which is less than 9. So x is between 0 and 9. And a couple more to finish up with here. Pretty much if you look at this, if b is a positive number other than 1, if you have this log, basically what this is saying is if the base is the same in both of them, if the log of x in that base equals the log of y in that base, then x has to equal y. So here's a numeric example, and then we'll do it on these two right here. Log of x in base 7 equals the log of 3 in base 7. You can kind of see that that x would have to be what that is right there. So if the log of x in base 5 is equal to the log of 7 in base 5, notice the bases are the same, then x has to equal 7 right there. Okay, so that's just kind of stating that property here. Now this is an inequality one. If the log of x in base 5 is bigger than the log of 7 in base 5, pretty much that has to be bigger than 7. And that's kind of stating that general rule. So we're just applying that to equations and inequalities. And that is lesson 10-2.